hopefully will look more and more like the green curve, right? That basically it'll just look like the baryon content, which looks like the halo mass. And in terms of the shape, on some level, this is what we see, right? That the magenta shape looks more and more like the green shape, except for a problem on the very high mass end. Because on the high mass end, the magenta curve kind of keeps moving to the right compared to the green, right? You know, here around a redshift of 4, the two sort of meet. At this point, I was just showing you ought to be this turnover into initial assembly. And then the magenta curve keeps going. And we start to see things that actually are more massive than you would be able to make if we just use the local universe matching between halos and galaxies, right? Or another way to say that, if I just take sort of a redshift 6 in this solid line halo mass function, okay, and I compare it with the measurements that we would get from SPLASH for galaxies that ought to live in these halos, you have too many galaxies. You have too many massive galaxies for the halos you ought to expect to be able to make by a redshift of 6. Okay.
Can you trust your masses to that precision?
Probably not. Probably not, and I'm going to come to that in a moment, right? So I think we can trust our luminosities. Whether we can trust the masses is exactly the question,
But even
right?
I mean, there's going to be there's a fair amount of, well, I guess there's not that much confusion in Iraq, but they're pretty faint, right? Like they're going to be, you're going to have a lot of contamination from nearby sources, right? Even in Iraq.
You mean something like blending, or do you mean incorrect redshift estimation?
No, blending. So
blending we definitely looked at, and is not big enough to account for this. So part of the problem is that if the masses are correct here, and if this is a pure number density problem, then the issue is it's an enormous number density problem, right? If you look at the scale here, I've got like 15 orders of magnitude on the y-axis, right? So the problem is that if it's just number density, then we're actually missing by many orders of magnitude. And if you kind of calculate what blending could do, certainly some of these objects could be contaminated, but not 99% of them. I think we kind of worked out the numbers, and it would be under half if you take kind of the very worst case scenario. I should also mention that SPLASH is not the only survey that can do this. So SPLASH is the best survey for looking at the high mass end because we have about 2 square degrees where we go very, very deep, which is just enough to be able to do this. Candles goes much deeper than SPLASH, but over a smaller area. And so they get an answer which is consistent with SPLASH, but because they have the smaller area coverage and we're looking at these rare massive objects, higher uncertainty. Okay. I should also point out that actually it's probably a little bit misleading to compare this with that solid line at a redshift of 6. Because this is telling you about the halos that exist at a redshift of 6, most of which on the high mass end just finished being made at a redshift of 6. Okay, so if it turns out that we can make most of the stars on the way in, so that by the time the halo assembles you kind of have a fully formed galaxy, maybe that's the right comparison. But that's probably not the case, and one of the reasons that we should expect that this is not the case is that if you really make most of your massive stars in small clumps, then most of their radiation reaches the IGM, and so we'd expect reionization at much higher redshift than current observational constraints. So if you imagine that instead, you kind of first have to assemble a proto-galaxy and then make the stars, and that takes a couple 100 million years at the star formation rates that we're seeing, then you actually should be comparing it with more like a redshift 8 halo mass function, and now we're missing by something like 7 orders of magnitude, right? So what this is really telling us is if it's just a number density problem, there's a big mismatch here, okay? Now, this is what I get from stellar mass estimates. If I go to even higher redshift where we don't have the Spitzer observations, and so we now have to take some mass to light ratio, then I can kind of push this out toward a redshift of 10. And then as you can see, as we go toward higher redshifts, the problem just is getting worse and worse, right? And it's getting worse sort of in every respect. In other words, it's not just that there seem to be too many galaxies. at a given mass. But the kind of everything looks wrong, right? The shape looks wrong. So the shape looks wrong in the sense that the mass dependence doesn't match, the redshift dependence doesn't match. You know, it really looks like qualitatively, the point is that qualitatively observations of luminous high redshift galaxies don't look like theoretical predictions for halo masses, even though we would expect that because there hasn't been enough time for these feedback processes to take hold, that, you know, everything the baryons are doing should look more and more like the initial assembly.
So what do you use to convert the stellar mass to halo mass?
So what we're doing here is, so this one actually you first have to convert a luminosity to a stellar mass with some mass to light ratio, but then we're still using some kind of redshift 0 derived answer, which also matches clustering measurements out to about a redshift of 4 where they can be done. So the redshift 0 and redshift 4 answers look pretty similar. So maybe that's another way to say this. In other words, to fix this problem, what needs to happen is somewhere right around a redshift of 4, the relationship between luminosity and halo mass needs to start changing rapidly.
So once this is what it does, why don't we take that out?
Yeah.
Yeah. So, and I think there are several places, there are several things that could be responsible for this, right? Certainly one possibility, you know, and maybe the most likely, is that these masses that we're inferring just are too high, okay? Something's changing in the mass to light ratio maybe. Maybe something's changing in the relationship between baryons and the halo. Maybe the stellar baryon fraction starts to go up sharply, right? In fact, you might even argue that maybe this is the signature of exactly what we were looking for, right? What we were looking for was this idea that at high redshift, as you get into this era of assembly, the main sequence should start to break down and something should look different about galaxies. Maybe the fact that if we sort of take the methods that work at lower redshift and blindly apply them to high redshift galaxies, you get this impossible looking answer is actually the signature we're looking for, that's telling us something starts to look different, right? Now there are some clues that there are some clues that these galaxies look normal. You know, they do have the properties that you would infer just by extrapolating from low redshift. And that's maybe a hint that we're doing something reasonable. But maybe what we're seeing is in fact just that the low redshift answer starts to break down, right? Certainly we were hoping that that would be the case around a redshift of 4, and that's where this starts to become a problem. Okay, if not, well, if not, then we're left with some other kind of more exotic answer, because if the points are right, then we need to move the lines instead. So that means we either need some kind of exotic high energy physics answer that's going to cause assembly to be more rapid than it would be under lambda CDM, or maybe some kind of exotic baryonic physics to cause the stars to run ahead of the dark matter or something like that. For the most part, by the way, this tends to be the opposite of what models people are thinking about right now will do. For example, in other words, cold dark matter tends to be about as good as it gets when it comes to assembling things quickly, because usually when you give dark matter interactions, what happens instead is you get something like thermodynamics, and then that inhibits structure formation, right? We would really need something that makes structures form more rapidly. Okay. What I would really like to say at this point is we're going to know the answer to this very quickly with JWST. Right? Because what's going to happen is we're inferring some properties of these galaxies from template fitting. We're going to get spectra. Either they're going to look like what we're inferring, and then you've got a problem with the halo mass function, or they're not going to look like what we're inferring, and we're going to learn that we've got the masses wrong. I should mention one other problem that I don't know how to solve, which is going to be critical with JWST, which is if this is telling us that the most interesting objects, now not just for galaxy evolution, but potentially for cosmology, are the most massive, highest redshift sources we can find, you have to find them. JWST, over about a 10-year mission, is going to see something like 2 square degrees of sky, about a 20,000th of the sky. Okay. Now, I could have said the same thing for Hubble. Okay. The reason Hubble has been so successful is because we do surveys with other instruments, and then we use Hubble to point at the interesting stuff. We need to do the same thing for JWST, and in particular, these most massive, highest redshift galaxies are going to be tightly clustered because they're going to live in the most overdense regions. And that means you're going to have regions where fluctuations on all different scales line up to give you the most positive contribution possible. Okay? And so what that means is, you know, here's an example of what one of these might look like, right? If you look at just these many sigma overdense regions, okay, if I point JWST at a random blank field, most likely I'm going to miss them, right? The median field will have 0. And then if you point it in the right place, then you find a bunch of the objects that you want to study. The problem is the only solution I've come up with for this so far is to use W first as the survey instrument. And
with HST too, you just have to, you just have to do dash, right?
well, but with HST you again have a coverage problem, right?
But you can still, if you did F160 and with like the drift and shift, you can cover all of Cosmos in like 60 orbits.
Well, but then,
It's just not going through the tag.
but then you need to, but the problem is that you need things that are probably going to be below the detection limit for that. If you're really looking for kind of these first galaxies, right, then you probably need something that Hubble's not going to be able to catch.
It can go pretty deep, even in like, an eighth of an orbit, you can still get pretty deep.
Right, but you're not finding, in other words, even in say a Hubble deep field, you're not turning up